Now we're going to look at the pond design. The first thing that I need to do is I'm going to figure out the total area. I believe it's 5.4, but want to double check. So I'm going to do a quick polyline around basically our project area. And we're going to have to determine, CL for close, we have to determine how much pond storage we need for our project. So I have 5.46 acres. So I'm going to bring over my Excel sheet and show you what I've got going on. So I have over here 5.46 acres. I am going to assume, because I don't have the time right now to do a whole, okay, so the impervious area would be, let's draw a line here. Well, I don't have the time to figure out all the impervious area for this short tutorial. So if I had to figure the area of impervious, I would look at the roadway, the alley, the sidewalk. I would have to look at the buildings, how much pond area we had, etc. So I'm just going to do kind of an assumption. For right now, my pond, let me squish up this so I can do side by side. So this is what I do at work. Between myself and the drafters I work with, we all kind of get bits and pieces. So somebody figures out the area of the pond, somebody figures out the area of the pavement, sidewalk, etc. So I know I've got 5.46 acres, and I know I've got a pond area. I'm going to use the bottom contour of our dry pond, and it's square feet to acres, 0.15 acres of pond. So that's not going to be 8% anymore. So I'm going to go ahead and go 0.15 acres of pond. Let's see what that percentage is. Equals 0.15 divided by that. That only equals 3%, and typically I would need 8% if it was a wet pond. So we'll see if 3% works or not. That means I've only got 95%, so I am going to up the pervious area to 25%. Okay, so now you can see that what I've got here. So let me, in Excel, let me go ahead and expand that. So I'm going to say it's I'm 200ths off here, so I'm going to let that be 25.3. There we go. You can't see the decimal places. I'm kind of a stickler for having all my numbers. When you're using Excel, there's no reason not to have all your numbers kind of equal out. So if I did, just to show you, everything has 2 decimal places, then that would make more sense. Now, my stage area, I'm going to go from 70, that's going to be my control water elevation. So that's the elevation that my orifice is at. That's going to let my water out slowly. And then it's going to be 71, 72, 73. And then I'm going to go ahead and add one more. Control copy, control paste. I'm also a little OCD about my spreadsheets to look nice as I go along, and the reason I do that is because I end up having to submit them to the reviewing agencies. So on 70, and this is why I have both of these open at the same time, on 70 the area here is 6539. 6539. 71, close. 71 is, I've already got the spreadsheet set up. 8223. 72 is the area of that contour is 11891. 73 is 13876. And 74, I'm going to go ahead, actually I'm going to go ahead and take this one and offset it 4 feet. And then I'm going to take this over here to get this to be 74 also, to make this kind of marry up. I'm just going to hit this perpendicular. Okay, and that gives me an approximate. Okay, so 74 is going to be 17054. Okay, now, so this is the acreages of each one. I also have a typo here, so that was 6539. Okay, now what that did is, if you look at this, all I did was take the square foot and divide it by 43560. So that's the acres. Now the volume, what I did is, the first one's going to be 0 acre feet. The next one, if you look at the formula, all I'm doing is taking these two values, the area, and dividing by 2, which is the average. So this is called the end average method. So I take the two areas that are on top of one another, that are, 71 and 72. I'm sorry, 70 and 71. And then I multiply it by the distance between the two contours, the 1 foot. Okay, that might seem like it's a kind of a stupid equation, because I know that there's only 1 foot, but sometimes I do things in multiple feet increments, like 71 to 74. So then it would be multiplied by 4 feet. But this one's 1 by 1. So I do that for each one of these. So now I take 71, 72, and then I take 72, 73, and then I get the end average area of 73 and 74. So now I've got what the volume is in between the bottom of this contour and the top of this contour. So basically what you're seeing is, if I drew a cross section, the pond looks like this, right? So I'm looking at elevations, the average elevation between these two, or the average area of this contour and this contour, to get an average in between, and multiplying it by an equal distance, by the distance between the elevations. Okay, that's called the average end area method. And then the next column is the accumulated. So all it does is the first volume, because it's flat on the bottom, there's no volume. Once it starts to stage up, then you can see I take the first volume and add it to the incremental volume, one contour up. Okay, and I keep doing that, adding it from the next contour volume to the next volume. Okay, so these are my accumulated volumes. So it starts out at 0. And at this first contour elevation, I got 0.17. At the next contour elevation, I would have, whoops, let me copy that. At the next contour elevation, I've had 0.40 acre feet, okay? And if I had the next contour, I would have 0.7 acre feet. In between this one would be 0.17, this is 0.23, this is 0.30, and then lastly, I would have one more contour elevation, and the total volume through here would be my 1.05. Now, I have to figure out in here how much water quality I have to treat. So there's 2 rules to South Florida Water Management District. Each district has different rules, but we're going to work in South Florida Water Management District. So South Florida has either 1 inch over the entire area for water quality, sometimes known as first flush, or 2.5 inches over the impervious, percent impervious. So 1 inch over the entire area is easy enough. 1 inch times 5.46 acres, and then divided by 12 gives me acre feet. Okay, that one's simple. The next one, not so simple. So the formula is, it's 2.5 inches over the impervious area. So the first thing you have to do is figure out the site area. So the site area is the total area minus the pond plus the building. And the reason we're doing pond plus building is because it's impervious, but it's not impervious that has, you know, if you're talking about a parking lot, it doesn't have contaminants on it. So the top of a building doesn't have to be treated for water quality. In ponds, because it's just water, the surface is just water, there's no water quality required, okay? No contaminants that need to be treated for. All right, so what it is it's going to take the area, total area, minus the pond plus the residential building area, okay? And then the impervious area is the site area minus the pervious area. So now I'm taking the site area from above and subtracting the pervious area, okay? So that gives me 62% impervious. Now, I'm going to take the 2.5 inches multiplied by the percent impervious, and the 100 is to convert it to percent, or to inches. And then I'm going to multiply, to convert it from the percent to decimal points. So then I'm going to multiply that value times the area minus the pond, because the pond, again, doesn't have to be treated. Okay, so from there I get acre inches, and then I have to divide that by 12. The next thing I have to do is look at which two is controlling. Which two are the higher values? This value here or this value here, okay? So what I did is, I don't know if y'all know how to use if-then statements. I used an if-then statement. So it evaluates, so I don't have to look at it. So that Excel program does the math for me. So it's just one step off my hands. If not, then you just look at it and you type it in. Now, South Florida has a rule that says you have to provide 150% above that. So I just took 1.5 times the greater value. So it says I need 1 acre feet of water quality, okay? Which is between the 73 and the 74 contour. So this elevation is going to be somewhere between the 73 and the 74 contour. So my pond technically really should be a bit bigger, but I'm not going to worry about that right now. So over here, I'm going to say 73, and I'm going to say elevation 74. At 73, I have 0.70. I'm sorry. The stage, I've got these backwards. Let me reverse these. No, I'm not. It's going to be one of those days. So this is going to be 0.7, and this is going to be 1, and this is going to be 1.05. Okay, so the elevation of water quality is going to be 7386. Okay, that's this elevation here. So this is going to be, and I'll write this, 73.86. Right, and let's see if I can bring that to the front. Wrong way. This is the other thing that I do when I give it to the district is I don't know why that's not working. Oh, I do know that, why it's working. There we go. I like to make these nice and neat so when you submit, the reviewers don't have such a hard time. And the top of the structure is going to be 74.00, which is basically the top of our pond. All right. From there, we have to figure out what size hole or what size orifice that we need to create in there, okay? The rule is you have, within the first 24 hours, only a ½ inch is required. The discharge in the first 24 hours is only a ½ inch of the required detention volume. So the total site is 5.46, and the pond is 0.15. So the total site minus the pond, and this is a formula from South Florida Water Management District. So the total site minus the pond is 5.31. So 0.5 times the 5.31 is going to give me, and then divided by 12 to get it into acre feet, is going to be 0.22. Now, that equates back out. So all I did is take the acre feet and divide it by the 24 hours. 24 hours, change it to minutes, multiply it by 60, change it to seconds, multiply it by 60. Okay, and you're multiplying the acreage, the acres by 43560, which converts it to CF or to cubic feet. Okay, so that's what that formula is. So it'll allow out 0.11. So now, to figure out the hole size that'll allow that much CFS, if you had hydraulics already, some of this might make a little bit of sense to you. So from the crest elevation, from that 73.86 to control, which is 70, and I've always got my spreadsheets set so it's kind of an easy path, linked path. See how it's linked up here? That there's 3.86 feet. Okay, between the two. And if I looked at the area, and this is a formula of a circular orifice, and I have to figure out the diameter, which the diameter of a circle is pi, or the area of a circle is pi r squared. So I'm looking for the diameter, so I rewrite this equation. So it says, based on this, my diameter is only 1 inch. But the rule is the minimum diameter that you're allowed to have for clogging purposes, because anything less than 3 inches clogs, is 3 inches. So this hole has to be 3 inches. And then I'll have to figure out what size weir this will let out for pre and post development discharge. Okay, so you can do a pre-development calculation of what you're allowed out. So if I did Q equals CIS, then I can figure out pre-development versus post-development. So if I had, let's say, and this isn't typically what we use. Typically we use NRCS, but for a quick method, we can use the rationale equation. Q equals CIS, since it's so small. For pre-development, we know we have a C of about 0.2, we'll say 0.25. And we know because it's all grass, 0.25. Actually, we'll go 0.3. And we know we're going to say a time of concentration. We're just going to use 10 minutes, which is going to equate to an I. And we looked at this last week, an I of 7.4, and then that will allow us to figure out, and we know our A is equal to the 5.46, okay, so our Q is going to end up being that times that times that. Okay, and we know in post development, I'm going to just highlight that, control copy, control paste, and I'm going to go post. So we know that we're going to probably have about a 0.65. Okay, I do have my handy dandy sheet over here, and I'm just going to assume single family. I'm going to go 0.6. So I'm going to go 0.6. Larger areas than about 20 or so acres, you definitely need to use the NRCS or the SCS method, but we'll accept this one for right now. So look at the difference. So in pre-development, we have a runoff of 12 CFS. And then in post-development, like I said, I'm trying to keep these all nice and neat. In post-development, we have double that. Now, out of our pond, we are only allowed out 12. So we have to hold on to approximately 12, right? So that's what this control structure does. It discharges out a certain volume of water. So there's also equations that allow a certain amount of discharge out. Here's an equation that we can use to estimate the size of this overflow weir. So for an overflow weir that's rectangular, let me clean this up. I just copied it from a different Excel sheet that I use. The pre-development would be the 12. The water quality control elevation is going to be the 7386. The top of my structure is going to be 74. So you can see that to allow out 12 CFS, it says that it needs to be 70 feet wide. So if that's the truth, if it needs to be 70 feet wide, and this is just an estimation, and the reason that this is such a large number is because this is such a shallow height. What we could do is at the 70.15, we could actually create, let's see how wide this is. I'm just going to use a circle. So if I do a circle, F3, and here, and I go D for diameter, and I go 70, then I could actually create an overflow weir, quadrant, perpendicular, offset that 70. So this would be the distance of my overflow weir. So if I looked at this, then I'm going to undo that. Then I could have up here at the top, F8, would be shallow overflow. Okay, so this would be a 74, and this elevation would be my 73.8. Okay, so water would just overflow this weir, and so that's what we're going to go with in this design example. Now this doesn't always work out because of stage discharge, but it gets you a first impression idea of what the weir equations and the orifice equations basically look like, and the assumptions that we use. So this one here designs our orifice here. This one here designs the weir structure at the top. But this just gives us an idea. I don't use this very much because it doesn't work out because of tailwater conditions and all that. So, but I do want to show you the weir equation that we use for the overflow. When you're doing this, make sure again your equations are properly set up. Okay, so you can take a look at this equation of how it's working. All right, so that is basically how we're designing our storm structure, or our pond, and how I use Excel to figure out the stage areas. Now I'm going to go ahead and adjust these layer properties. I'm going to create a new layer, 0-FAU-pond. Set that to blue, cyan. Doesn't matter what color. We'll end up having to change like these probably to different colors anyway to get them to print properly. So what I'll do is, as I go through these videos, I'm not printing out sheets, but I will at the very end kind of collate these into actual construction plans and show you how to do that also. Okay, so there's my pond for right now. All right, in the next video, I'll show you how to do the storm to get the the pipes out to collect the water and bring it to the pond for our site.